I want to talk about reasoning models, and in particular two ideas. One is speculative decoding, and then the other is the key idea behind some of the most recent breakthroughs in reasoning in the all model series at OpenAI and DeepSeek's R model series. So, and by the way, also Google. I mean, to give credit to Google, both seminal papers I'm going to discuss today. One, the speculative decoding paper, which came out of Google, and then also the chain of thought paper, which came out of Google. So no matter what you think about Google, I think the work that is done there from a scientific perspective is really, really amazing. The papers are in the show notes. So let's start with speculative decoding. The idea of speculative decoding is to replace some of the transactional resources that a system needs with computational resources. So you have enough compute that is idle because of data movements. So what if we could replace that by having more compute, doing more things at inference time, and then having some sort of mechanism that can decide what of that additional work is useful and what isn't. In other words, you create a sort of a parallelized branch of potential tokens and then pick the ones that are good. And then the idea of reasoning in general is the automation of chain of thought. That's really what the fundamental idea is. So how you do it, whether you do it with reinforcement learning, like in R0, where you use no priors or you use some priors, or whether you do it with Monte Carlo search, that is different, obviously also a very important question. But fundamentally what you're trying to do is, so this chain of thought, which 2022 paper, which really made sort of the big headlines in Europe's 2023. And then you want to use that concept of chain of thought to have more advanced reasoning models. This is not even on podcast. It's February 4, 2025. This is Krim Delco for the day. The fund is up 2%. The market is up 75 basis points. Really, we're down 5.1%. The market's up 2.5%. We're underperforming by 7.6%. So reasoning models are all the rage, I think, for good reasons, because now we're really approaching really powerful intelligence. I wouldn't call it human intelligence, or maybe you can call it AGI, but not human intelligence. I think these comparisons are misguided, but it's just really important, interesting work. So let's start with speculative decoding, and then we're going to talk about general reasoning models. And I think the purpose of this podcast is also give a little bit of a history of where these ideas come from. It's like what we do here at Launch Capital Partners very often is we like to sort of trace back the academic history of people, of ideas, of models, of even businesses sometimes. And I think this is a good example where, okay, well, where is this reasoning coming from? What actually is it? And if you go back to the source, which is, let's say in this case, the chain of thought paper, again, a link in the show notes, you kind of understand a little bit what it is. We don't know exactly, let's say, what OpenAI is doing with O1. And we haven't studied deeply what DeepSeek's doing with R, but we have a good idea of what the fundamental ideas are, and that's really the purpose of this podcast. It's not a technical podcast. The purpose of this podcast is to give people a sense of what it feels like to run a hedge fund. So you might think, okay, why are we talking about reasoning models here, of course? Well, it's because if you understand what the future technology of AI is going to look like, I think it's going to be really helpful in terms of making investment decisions. So what is reasoning really? Reasoning is, in technical terms, is you apply more compute to get more out of pre-trained models. So very importantly, you're not changing the model. So if you train, let's say, a GPT or Llama or Claude, like, there's a world of pre-trained models or foundation models. Like these models, they spend months and months and months and train a large amount of data. They use autoregressive transformers to train those models. Those are pre-trained models. So very importantly, pre-trained models are models that are sort of a compression of knowledge. So that's for one, right? You have the knowledge of the internet compressed in latent space and searchable and tokenized. So that means the machine can access that knowledge in a particular way through autoregressive inference. Now, what chain of thought does, it extracts more knowledge from that base of knowledge through chains of thought. So through particular prompts, it gets more or different types of knowledge out depending on what kind of chain of thought it uses. And this is very akin to humans, right? If you read a book, you can analyze that book by asking yourself particular questions about the book. And if you ask different types of questions, you will get to different types of conclusions. So this is very similar, and I think, and that's why it's so exciting. I think that, we talk about human level intelligence, literally intelligence that looks and feels like human, because that's what we do. Now, whether that's the whole story or not, I don't want to go into that conversation, but it's really powerful to have a system in place that, again, can extract different types of inferences from a given model. So this is what chain of thought is saying in its fundamental form, right? The paper is not even saying it's better or worse. Of course, it's better and it beats benchmarks and things like that. But what's more important is that you can have a model, let's say Llama, and with different prompts, you can get different results without changing the weights of the model. You don't have to retrain the model or anything like that. And that's the key idea behind chain of thought. Now, speculative decoding is, in a sense, similar, and the paper goes back a couple of years more, I think. I'm not quite sure, but it's a bit older. The idea of speculative decoding is, I would say, it's a milder version of chain of thought. And what speculative decoding means is it's actually an efficiency tool. All it says is, look, when we do inference, we have to run k runs to get k tokens. And that's fine, but how about, what if we could get more than k tokens in one run? How could we do that? Well, we could speculate. We could have, and the paper actually talks about it, they rely on something called branch prediction in chip design. So that is kind of, you already anticipate what the next few tokens could be, right? So when you generate at inference time, you're running your token predictor, and instead of just doing one token, the best token that the model comes up with, you have a branch. And now think about it, like you could have thousands, millions, billions of branches. And then you could have a model. Actually, I don't know how many there. Maybe that's probably a parameter you can fine tune. But the point is, you can parallelize this, right? You can have lots and lots of branches, and now you need some sort of classifier, and the classifier is embedded in the base model. And there's some sophisticated statistics that you can borrow from the base model, which then decide which of the speculative tokens are good and which aren't. The key is the following. Like when you have k runs of token predictors, what you want is at least k, if not more than k tokens predicted, and the quality to be the same. That's what you want. And that's what you get in the according to the authors. So now, borrowing this idea of speculative decoding, let's go to the reasoning models. They're doing more than just increasing efficiency, but they're kind of doing the same thing in the sense that they're speculating over a bunch of possible chains of thought when they try to solve a problem. And I think what I like about the reasoning models and the way they're set up, and we discussed a recent paper that was published at NeurIPS about this, where we spoke about the sort of automated chain of thought and the templatizing of problems and things like that. We're going towards the actual holy grail of AI, which is solving problems, right? Nobody builds a model in order to generate tokens. We don't care about tokens, the same way we don't care about branches in in chips, right? What we care about is computations in chips, and we care about problems solved in AI. So if we have, let's say, just for example, we have a problem that needs to be solved, which has kind of the feel and the look of a quadratic programming problem, then the branch predictor or the token predictor or the inference engine or whatever you want to call it runs, these several possible chains of thought, and the best one would be the one that actually applies, quadratic programming solutions to the problem. And the key of the model is, of course, to identify this and then apply the actual template of quadratic programming to the problem and then solve it. So that requires, of course, that these models have to be trained in a way so they can recognize problems. And I think that is, one of the courses we're sort of attending, not fully. I mean, when we say we attend courses at Stanford, that doesn't mean we're not graduating or anything, but we do, read papers and sometimes go to class and sometimes just go to seminars and sometimes just participate on Zoom and things like that. But the idea is there's a class, a sort of self-evaluating systems, and I think these are all cousins, right? A self-evaluating system in the context, let's say, of this class it will be something like a website, like an agent, an agentic system that can, maybe go and book you a flight to Europe and also get you hotels and things like that. So the system can self-evaluate and self-decide what's the best way to solve the problem. So the key, of course, is self-evaluation, and I think I want to stay with that because I don't want to branch out too much here. When you build a reasoning model, or when you train that reasoning model, in order to, like I just said before, let's say identify the nature of the problem and then apply the template that is necessary to solve the problem. When you do all these things, you need to have some sort of eval. You need to be able to evaluate these models in such a way that they can discriminate and say, okay, they have to have a way to say this is better than that, right? That's the key, and that's what's called eval. This is better than that. And without going too much deep into the weeds, but let me just say a few things about reinforcement learning, right? Reinforcement learning as a tool now. Reinforcement learning is really the idea is to optimize a path within possible solutions, right? So if we have a reasoning model that is being trained on identifying possible paths towards a solution, then the reinforcement learning can be the tool that helps us actually get the most optimal path for a particular solution. That's what R0 looks like to me. It's a reinforcement learning methodology applied to a reasoning model. So to summarize, speculative decoding and reasoning models are cousins. Self-evaluating agents are also part of that. The whole idea is like what we're doing here and where we're going as a field is we're creating models now that have the ability to identify a problem, to self-evaluate what the best route of solving the problem would be, and then solve the problem. And they can do this in parallel. So they can do it fast, and they can do it at a relatively low energy budget and cost per token budget. Thank you.